Chapter begins with a little bit of a review from Chapter 1, Chemical and Physical Changes. In this chapter, we look at only chemical changes, which are known also as chemical reactions. Our objectives for the first section are to learn to correctly write equations to represent reactions. These equations can be written in word form or formula form. We also will look to identify whether an equation that's written is balanced or unbalanced, and if it's unbalanced, to balance it properly. So we'll be looking at all of these things through the PowerPoint today. Beginning with a chemical reaction, which is another name for a chemical change, is a process by which one or more substances are changed into one or more different substances. The basics behind this: chemical bonds within the compounds are broken, the atoms are shuffled or rearranged, and new bonds are formed between different atoms, creating new substances or new compounds. Now, the new substances will have totally different chemical and physical properties from the ones we start with. In other words, when you look at the new substance, you will not recognize the original stuff you started with. Of course, there are several signs to use to identify whether a chemical reaction has taken place. For example, evolution of heat and light, in other words, fire. Change in temperature. If a change occurs where there is heat energy given off into the environment, it's called exothermic. And if heat energy is absorbed from the environment, it's known as endothermic. Another sign of a chemical reaction is the formation of gas bubbles that weren't there before. For example, vinegar and baking soda are mixed. And formation of a precipitate, which is a solid that forms when two liquids are mixed. For example, in this picture, you see two clear liquids mixing to produce this solid yellow substance. That's the precipitate. In cooking, we often see chemical reactions that result in changes in color or production of odor. And in some things like glow sticks, we see light given off without a change in temperature, and this too could be a sign of a chemical reaction. This process is known as chemiluminescence. Chemical equations are used to represent the chemical reaction or chemical change that takes place, and they can be written using words or symbols, which show the identities and often the amounts of reactants and products in the chemical reaction. It's basically a shorthand way of writing what's happening in the reaction. For example, sodium metal, which is in this glass jar down here, reacts with sodium gas, which is that poisonous gas right there, and it creates what you would think of as an explosion or an exothermic reaction to produce sodium chloride. When writing equations, they must represent everything that we know as fact, and they must contain correctly written formulas for all reactants and all products. Additionally, they have to satisfy the law of conservation of mass. So let's take another look at this reaction. Sodium is written as Na. Chlorine is written as Cl2 because chlorine's diatomic. And it creates sodium chloride. And we know from our chapter on naming compounds that sodium has a 1+ charge. Chloride is a 1- charge. So the formula is NaCl. Now, does this satisfy the law of conservation of mass? Well, do you have the same number and same types of atoms before as you do after? And the answer is yes to types, no to number. You started with 2 chlorine, but you only finished with 1. So we know that there's more work to be done to write this equation right. Okay, I mentioned that the equations can be written in word form, which are much more vague, and the amounts of the substances are implied, not stated. But when writing a formula equation, it has to be a little bit more specific. We need to get into the actual numbers of each substance. Here are some more examples. We have magnesium plus oxygen yields magnesium oxide, a common reaction in many fireworks. We have 1 atom of magnesium to start, 2 atoms of oxygen to start, but we finish with only 1 magnesium and 1 oxygen, so that tells us that this equation is not yet written correctly. In our next example, photosynthesis, you have carbon dioxide plus water yields glucose and oxygen. Take a look at the numbers of each element. You start with 1 carbon, but you finish with 6. You started with 2 hydrogens, but finished with 12. Oxygens, we start with 2 here and 1 here. That's a total of 3. And we finish with 6 there and 2 there, so that's a total of 8. Taking a look at the numbers, it looks like we're creating a lot of atoms from nothing, so we know that this is not quite written correctly yet. Now, look back at the terms I've been using. The stuff we start with are called reactants. The stuff we finish with, that's what's created, that's our product or products. In a math equation, we use an equal sign, but in our chemical reactions, our chemical equations use an arrow instead of an equal sign, and it's read as yields. There are a variety of other symbols that we place in there to make sure we represent known facts. For example, we can place any of these symbols in parentheses after an element or a compound to show what state it's in. The first three are a little more common sense. We use S, L, or G in italics and in parentheses to show that it's a solid, a liquid, or a gas. AQ is a very common and very important one that shows that the substance is dissolved in water. So we call this an aqueous solution. The last two I hardly use because there are other ways of doing it, but you may see an upward arrow in our textbook that represents a product that's produced that's a gas, and a downward arrow represents a product that's produced that is a solid. You can also do the same thing by just placing a G for the upward arrow or an S for the downward arrow, and that's what you typically see in a lot of books and a lot of worksheets. Okay. The symbol for the arrow could be changed, showing conditions that we need for the reaction to take place. Our standard arrow just means yields. If you see a double arrow, you are looking at a reversible reaction. In other words, the products will go through a reaction and recreate the stuff we started with. You may have to heat the reactants for the reaction to take place. If there's heat involved, we put either a delta over the arrow or write out the word heat over the arrow. If it's a temperature that's needed for the reaction to take place, we can actually just write the specific temperature. And for pressure, we can do the same thing. If we need more than standard atmospheric pressure, we just write the word pressure over it. But if we need a specific pressure, we write it over the arrow. The last one occurs with a formula written over the arrow. This shows that we need that compound to act as a catalyst to cause the reaction to take place or to alter the speed at which it takes place. Now, the law of conservation of mass states that whatever atoms we start with, we must finish with the same numbers and types of each. An equation that meets this requirement is said to be a balanced equation. We sometimes have to balance them by changing numbers or changing the amounts of each substance until we have equal numbers of atoms of each element on each side. We balance equations using coefficients. Think of coefficients in algebra as a number that you multiply through all of the variables after it. It's similar in chemistry. Let's say you see 2 sodium chloride. That means that you multiply the 2 all the way through the formula, distributive property you might say, and you have 2 sodiums and 2 chlorines. All right, these are just a few guidelines to get started. We learn many more tips and hints along the way. First, when you have a word equation, be sure to write the formulas correctly in the equation when you go to the formula equation. This is especially important to remember the diatomic elements. These are the ones that are unstable and can only exist in pairs. Next, begin by listing each element under the equation and recording the number of atoms of that element on each side of the equation, the left and right side. Begin adding coefficients as necessary, but every time you add a coefficient, recalculate the number of atoms of each element and record the new number. Balance hydrogen, then oxygen last wherever possible. Now that should be a guideline that said, because it says wherever possible, you may not always be able to use that guideline, but you should always attempt to balance it with hydrogen and oxygen last. I mentioned the diatomic elements. Those of you that sat in front of me in class remember my trick for the diatomic elements, and that's Janine Hunkelbrief. These are elements ending in GEN or INE. Hunkelbrief is the list of all of the elements: hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. Astatine is also on the list, just very rare, so you probably will not see it in this class. All right, so that means whenever you see these, you write them in this form. So let's take a look at that equation from earlier and figure out how to fix it. Looks like we have the right number of magnesiums on each side, but somehow an oxygen atom disappeared. So ask yourself, how many units of magnesium oxide could you make based on the 2 atoms of oxygen you start with? Answer is 2. When I multiply that through the magnesium oxide, I get 2 magnesium, 2 oxygen. All right, go back now. Our oxygen's good, but we don't have enough magnesium to make 2 units of magnesium oxide. So we need to start with more magnesium. In the last one, we were just learning to crawl. This one, we're kind of learning to run. But look at your total numbers. You have 1 carbon to start, 6 to finish, 2 hydrogens to start, 12 to finish, 3 oxygens to start, 8 to finish. Okay, you want to do hydrogen then oxygen last, so begin with carbon. You have 6 on the right, we want 6 on the left. So I'm going to put a 6 in front of carbon dioxide. And remember, that means you have 6 of that whole unit. So 6 carbons, and for oxygen, you have 6 times 2 is 12 oxygen, plus the 1 over there gives me 13 oxygen. Carbon's taken care of, go to hydrogen next. You started with 2, you finished with 12. So 6 times the 2 waters will give me the 12 hydrogen I need. But remember, we're multiplying it all the way through. So that's 12 hydrogens, but now that's 6 oxygens. 6 oxygens with water, 12 oxygens with carbon dioxide gives us a total of 18 oxygens. Now, on the right side, we have only 8 oxygens. Do we put the number in front of glucose or in front of oxygen? Answer, oxygen, because putting in front of glucose will alter everything that we already balanced. So, how many oxygens do we need here at the end so that when we add these 6, we get the 18 we need? The answer is we need 12 here. Putting a coefficient of 6 in front of the oxygen gives us the 12 we need, so that when we add on 6, we get a total of 18. Let's try a few more examples. First one, you have 2 sodium, 2 oxygen, 2 hydrogen to start. But we finish with 1 sodium, 1 oxygen, and 1 hydrogen. Okay, save hydrogen, oxygen till the end. Often they'll balance along the way. So to balance sodium, put a 2 in front of sodium hydroxide. That gives you 2 sodiums, 2 oxygens, 2 hydrogens, and it looks like everything else balanced along the way. In the next equation, we have carbon, sulfur, and oxygen on each side. We start with 1 carbon, finish with 1 carbon. Start with 2 sulfur, finish with 1 sulfur. Start with 2 oxygens, finish with 4 oxygens. 2 there and 2 there. All right. Save oxygen till the end. Carbon's already balanced, so we start with sulfur. You have 2 sulfurs on the left. On the right, we need 2 sulfurs, so I'll put a 2. That increases sulfur to 2. It changes that number of oxygen to 4. But remember those 2 over here. 4 plus 2 gives me a total of 6 oxygens. Carbon and sulfur are balanced, so we fix oxygen by putting a 3 there. And 3 times 2 is 6. So carbon, sulfur, and oxygen are balanced. All right, what if you're given a word equation and asked to find the formula equation and to balance it? Well, in this particular one, we have to remember everything we learned about writing formulas. Begin with barium chloride. Barium is a 2+. Chloride is a 1-. So the charges don't cancel. Cross them, and we get BaCl2. Now, it says aqueous, so I put an AQ after it. And I move on to the next substance. Sodium chromate. Na is 1+. Chromate is CrO4. 2-. Charges don't cancel, so we cross them over. We get Na2, CrO4. That's also aqueous. What does it yield? Barium chromate precipitate, so that's a solid. And barium is 2+ and chromate's 2-, so that's BaCrO4. solid plus sodium chloride. Sodium chloride is NaCl. Sodium's 1 plus, chlorine's 1 minus, and it says aqueous, so I'll put an AQ after it. Now, here's the first of the many tricks you'll learn. When you're listing the units of each, you have 1 barium to start with, 2 chlorines, 2 sodiums, and any polyatomic ions that appear on both sides, like we have here, can be kept together as 1 unit. So I have 1 chromate. Now when we do this on the right, list them in the same order so that you don't get confused. Looks like 1 barium, 1 chlorine, 1 sodium, and 1 chromate. Looking these over, we need to balance chlorine and sodium, and we can balance both of them by placing a 2 in front of sodium chloride. Perfect.